It's really great to have Nikhil Bansal here. Nikhil is the Patrick C. Fisher Professor of Theoretical Computer Science at the University of Michigan. Nikhil got his PhD from Carnegie Mellon, advised by me. It was really a case of, a student does great things, comes and tells you what they're doing, and you say, wow, that's great. Keep doing whatever you're doing. So then he went to IBM and became manager of the algorithms group at IBM Watson. And after that became a professor at TU Eindhoven. In 2021, he came back to the US, joining the University of Michigan. Nikhil's won a number of awards. Best Paper Award at Fox, twice Best Paper Award at ESA, twice the IBM Pat Holberg Research Award, and is a fellow of the ACM. And he's well known for his work in algorithms, combinatorial discrepancy, combinatorial optimization in general. And today he's going to talk about Quasi-Monte Carlo integration discrepancy. Right.
Thank you, Abram. Great to be here. Good. So, yeah, today I'll be talking about kind of these two desperate areas, Quasi-Monte Carlo integration. I only learned recently about this thing, so I'll give a big overview of what this is all about. And this area of classical discrepancy theory. And this is joint work with Haotian Jian, who's right at U Chicago, right here. I guess he couldn't make it today. Good, so let's get started. So the talk will be about like numerical integration. And the setting is, we have some function and we want to integrate it over a domain. And usually here you can assume that the domain is kind of in a standard form, right? Just assume it's a unit cube. You can always apply some transformation and bring it to this form. So we'll always be like looking at this problem. So usually when you want to do this, exact evaluation is pretty not so usually possible. Your f could be too complicated, or you might have only like query access to f. Right? So the standard thing is to just pick a bunch of points, evaluate your function, and output the mean. So what do people do in practice? So there's one way which we all know, like the Monte Carlo method. Just pick these points at random. Right? So each of your sample is kind of an unbiased estimator of this mean. And we all know that if you take n samples, the error will start to scale as the standard deviation of f divided by square root n. Right? Or in other words, like the number of samples you need to get epsilon error kind of scales as 1 over epsilon square times the variance of the function. Okay, and the whole goal in like statistics or whatever is to minimize the number of samples, because samples could be expensive. Also, if you're doing an experiment, it means more running time and so on. Okay, so what's done? So there are two approaches to kind of improve this dependence. So one, which will not be our focus, is the variance reduction techniques. So these techniques kind of target reducing this by sampling more smartly. And again, there's like a whole zoo of these techniques. Maybe some of these things are things you've heard of. But usually they require knowing some additional information about f, right, to kind of use them effectively. Okay, so there's a second method, which maybe is less known in TCS community. It's what called, but it's again like a huge area for the last 50, 60 years. And I'll talk much more about it. So these are like called Quasi-Monte Carlo methods. And these aim at this dependence, like trying to improve the square root n dependence in Monte Carlo. So the big result here, and we'll see how this comes about, is that you can get a rate which is roughly like 1 over n. And tilde here means typically polylogarithmic factors, which we can ignore throughout this talk. And this might make sense. So for example, let's say your function looks something like this, and it's a one-dimensional function. So it might make sense to like place points equally on this line and then take the average, right, instead of random points. And you would expect that the error, like you pick up half the contribution from here and half from here, so the error would start to go like 1 over n, because of maybe this point is somewhere in either side. Okay, so that makes sense, maybe you can do that. But then if you think about it for a moment, you realize maybe this is not, does this even make sense, right? So suppose I fix a bunch of carefully chosen deterministic points, right? So let's say like this. Then I can always concoct a function which does very badly, right? Because the integral of this function would be like half or whatever on this average. but maybe you're just unlucky and you pick all the sample it at all the wrong points. Right? And what's kind of interesting about this example is that if you look at the standard variance of both these functions, they are the same, right? It's like theta of 1. So Monte Carlo would do basically the same kind of error for both. But if you choose these deterministic points in Quasi-Monte Carlo, you can do pretty bad. So what's going on? Like, can we even say anything meaningful in this setting if you pick these fixed deterministic points? So it turns out you can, and this is kind of the main result in this area. So if you change your notion of what variance means, and we'll define this later, but for now, let's denote this quantity sigma of fhk, it's called the Hardy-Krauss variation. Then the theorem in this area is that your error scales roughly as 1 over n, right? And then there's this dependence log n times the dimension minus 1. But think of it like the settings you're interested in is like small dimensions, 3 or 4 or whatever. So this is negligible. So the error rate kind of goes down like this. Okay. And this is widely used in like all kinds of practical fields, finance, physics, especially where you have like low dimensional problems, or in like graphics, where you care about 3 dimensions. So on, and again, like tons of books on these things. Good. So my plan is to give you first like a quick overview of this area, what it's all about. Like there's sort of some very beautiful ideas. And the starting point of this thing is this very exact formula for the error. So let's just look at the one-dimensional case where we'll draw a picture. Yeah, so we'll always assume that our domain is like 0 to 1. And you are integrating maybe some function. Right. And I'll denote x, capital X, as like the set of these endpoints where you're evaluating this. So it turns out like no matter which set of endpoints you pick, you can get the exact formula. So this is an equality. But it says the following. So if you look at the error between your sample average and the true average, it's given by this quantity. So f prime is the derivative of f. Times this thing called the dx, which is what's called the Lebesgue discrepancy function of how well these points are placed. So let's see what this means. So suppose I place these red points. So d of x is defined as, so I'm placing n points in this interval. So if I look at, say, any prefix interval 0 through x, so I look at n times like the continuous measure of this interval, n times little x, minus how many points fall in that interval. Right, so this is going to be a crucial definition for us. It makes sense. So it's kind of like how imbalanced you are, right, for this interval 0 through x, from the true measure versus like how many points are falling. And if you like place points equally at distance 1 over n, this function is at most 1 at any point. Good. So, okay, and so maybe this formula looks mysterious, but it's like completely trivial to prove. It's just a like application of integration by parts. Again, if it's been a long time since you saw your calculus, the integration by parts formula. So it basically allows you to, you're integrating a function u dv, kind of allows you to swap v and u. So let's see why that happens here. So, we are interested in this error between the sample and the true error. Now I can think of this f bar x, by definition is just evaluation at these points at 1 over n. So I can think of kind of this measure mu of x, which is putting, like 1 over n Lebesgue measure at each of these points x1, x2, so on. Right. So I can write this error just as f times like the difference of these two measures, and if I just do integration by parts, you will get the derivative here and the integration there. And if you stare at it for like a few seconds, you realize the integration of this is exactly this function. Good. So this formula will be kind of important for us, and I think this was discovered even in like 50s and 60s. It has a name, Halab-Karzurumba formula. Now, why is this interesting? Because everything generalizes very nicely to higher dimensions. So again, if you do like 2-dimensional integration by parts, you'll get like this error. It's kind of the natural thing. So now this function, this discrepancy, Lebesgue discrepancy becomes, so I look at a point xy here. Then I kind of look at this red rectangle, anchored at the origin and this point xy. And d of xy is, so I'll call this rectangle r of xy. So it's kind of the natural thing, the analog what we had for intervals. So you look at n times like the area of this thing, that's the continuous measure, minus how many points fell in that rectangle. So that's my measure of like the imbalance or discrepancy. And you can think of this as a function, right? Like as I vary x and y, this is like a different value. And so this error is just the integration. Right? And this f of x y denotes like the second partial derivative with respect to x and y. Actually, if you do this, so in one dimension it was pretty simple, but if you do multi-dimensional integration by parts, you'll get also like exponentially many terms, like 2 to the d, because for different low dimensional faces and so on, but let's not worry about that. So morally it looks something like this.
Yeah. These terms appear when you have points on the boundary, or also without points on the boundary you still have those terms?
Even without points on the boundary. So typically, you never need points on the boundary because it's a low dimensional thing. But what will happen, because in integration by parts, the thing we conveniently ignored, there is this thing, and if you do it like multiple times, those boundary things start to affect you. So what will happen is basically, you will get like a term which corresponds to integrating over this face, and you look at rectangles which are 2-dimensional. So again, it doesn't matter. So throughout this talk, we'll only care about kind of the one-dimensional thing, but I just want to show you, there's like, this whole theory generalizes to higher dimensions. And yeah, so we'll never worry about what is this exact form, but there is an exact form. Okay. So I said, yeah, let's just only worry about the one-dimensional case. So this is the true error. And what people in this area do, like this is the key sort of inequality, if you open any book on this thing, like the first section 1.1 will be about this inequality. It's called the Koksma-Halavka inequality. And it's just applying Cauchy-Schwarz to this thing. Right? So you just say, okay, my error is bounded by this 1 over n times the L2 norm of this discrepancy function times the L2 norm of the derivative. And now these things have names. So this is exactly what's this Hardy-Krauss variation, the L2 version of the Hardy-Krauss variation. And this thing we'll call the L2 Lebesgue discrepancy. So any questions about this formula? Because this will be like a main character of our talk. So basically your error is 1 over n, which is great, and then determined by these two things, Hardy-Krauss variation and how well your points are placed. Okay, so this is compact way of writing it. And there's also like, so we'll mostly look at the L2 version. People can apply any kind of holder with any norms. So you can look at the L infinity L1 version. So this is also studied and so on and so forth. Morally, these are all roughly the same because these things, they don't change by beyond logarithmic factors. And L2 will give cleaner bounds, so we'll work with L2. And again, you can define all of these things in higher dimensions, but as I said, we just worry about the one-dimensional case. I mean, one-dimensional will suffice for all our ideas. Okay. So this Koksma-Halavka inequality is actually tight in general. So if you give me any placement of points capital X, I can concoct a function where you can't improve this. It's kind of tight, right? So this suggests maybe most of the only game I can play is kind of coming up with good placements of points X. And this is what's kind of been going on in this field. So, right, so for one dimension, actually this problem is trivial. I mean, what are you going to do, right? Like, there's not many other candidates for uniform placement other than just placing them like regularly at uniformly spaced intervals. But this already gets very interesting in 2 dimensions. So let's test our intuition. So our question is, I want to place n points, let's say in a unit grid or a unit box. So maybe, and I want to do it kind of uniformly. So maybe this is a very natural candidate, just place them in a grid. So what's the discrepancy of this placement? And let me write the definition of this. Yeah, so definition is right on the top, but let me draw it pictorially. So if I look at any point x, y, I look at this rectangle, and the discrepancy is kind of the n times the volume of that rectangle, which is just nxy minus the number of points.
Root n.
Okay, why?
If you take a rectangle which has height 1 over root n and like width 1.
Good. Exactly. So this thing has about root n discrepancy. Indeed, and because I'm placing n points, so the distance here between any two layers is 1 over root n. I'm placing root n by root n grid. So the area of this rectangle is times n is like root n. So as I vary, from here to here, you are picking up this quantity is changing by root n, but the number of points are not changing. So typically, your dxy will be like root n. And this is bad, right? Because if you recall the formula for error, kind of discrepancy, okay, doesn't matter whether it's whatever, it's all the same thing. So this guy is like root n. So you are getting like 1 over root n dependence, which is kind of the whole point of avoiding that in Monte Carlo. Right? Okay, so it's basically no good than random, no better than random. Turns out you can do much better. And this was kind of this maybe observation that started this field. And in particular, there are these very explicit point sets. So one of them is called Vanderkorpert set. It was discovered in 1935, almost 100 years ago, which gives you an exponential improvement. So the discrepancy of this point set is log n, as opposed to root n. And actually, if you stare at that, the points really kind of look, in some sense, more uniform, right? Maybe I forgot to mention. So if you actually look at random points, so this was a picture, the same picture of 64 points randomly placed in a grid. This looks like much more random. Somehow, yeah, these very explicit points can actually work much better. Good. And what's very nice about this point set is it's completely explicit. So in fact, here is the whole formula. So n is let's say 64 point of placing. So I vary my x coordinate as 1 over n, 2 over n, 3 over n. And the y coordinate is just, you look at this I in binary representation and you flip the bits. So you just reverse it. So 0, 0, 0 and become 1, 0, 0. And that's it, that's the whole construction. Right? So I don't know, Vanderkorpert was thinking about these things already 100 years ago. But it's amazing, right? So it's very simple to construct, it's completely explicit, you can just use it. Good. And actually, when I say log n discrepancy, I even mean the worst case discrepancy. In fact, the L2 discrepancy is log n. And then you might ask, okay, log is great. Can I get a constant? So it turns out there was this big result in this area by Roth. He was actually a Fields medalist. And he started this whole area of geometric discrepancy using Fourier analysis. And he showed that, you can't really beat root log n. So this is tight. And even in general dimensions, D, this is the answer. And for infinity norm, this was again later improved. And it's still actually open to close the gap for D greater than 2. So this is what they call the great open problem in this field. So this log n matches for D equal to 2, the lower number bound, but for higher dimensions. So again, these are the kinds of things people look at in this area. Here is actually another cool construction. It's called a lattice rule. And again, a very explicit set of points which gets the same bounds. So again, I vary my x coordinates in intervals of 1 over n. And then I pick an irrational number, let's say the golden ratio. And then I just look at multiples of that, but modulo 1. So it's kind of like a lattice, but projected into the unit thing. And again, this gives an amazing placement of points. And this kind of thing works for, in fact, any rational number. But what's nice about the golden ratio is that if you look at the continued fractions of this, they're all very small coefficient. It's 1, 1, 1, 1, 1. And that somehow figures out in these bounds. So it's a pretty actually deep area and Diophantine approximation and so on. Yeah, we can prove such results. And again, in this Quasi-Monte Carlo thing, there have been tons and tons of other constructions. So these are just the two I showed you. they generalize to higher dimensions, various other ways of doing it. Like tons of books on these things. Okay, so that was Quasi-Monte Carlo. Like, any questions about? Yeah.
Just a small question. So this game of placing the point is completely independent of the function.
Exactly. Yeah. So you're just decoupling. Yeah, I will place points, and then I'll just integrate. I don't need to do anything about my function, or at least that's the way these people look at it. Good. Okay, so let's kind of compare these two things, right? So really we should think of Quasi-Monte Carlo if I'm using a good placement of points, polylob discrepancy. Roughly I'm getting this rate of error, and for Monte Carlo I'm getting with this root n rate of error, but with a different notion of variance. So of course, like one drawback in Quasi-Monte Carlo is that this Hardy-Krauss variation can be much larger than the usual standard deviation. And one way to see, like again, matching our intuition, if your function was very variable, like sine kx for large k, so it fluctuates a lot, then the derivative of f prime would be k times like cosine. So it's like Hardy-Krauss variation will be roughly k. Hardy-Krauss was the L2 norm of the derivative. So it's not always better, yeah. So Quasi-Monte Carlo is bad. Another problem with these things is these point set constructions are very delicate. Like even if you fudge them slightly, like things can like totally break down. So they really depend on these very delicately choosing points. But in like many applications, this may not be possible, right? Like maybe you're just getting random samples from somewhere, or in statistics things, maybe like these points correspond to picking a person from a population and doing some measurement. So I can't say like, get me the person corresponding to this particular coordinate. Like, does not make sense. So that's one drawback. The other thing is also it's like deterministic, so you can worry about worst case outcomes and so on. So okay, so there's a natural question: can we combine the benefits of both these, like Monte Carlo and Quasi-Monte Carlo? Can we do better? And again, we are not the first ones to ask this question. People have in this community thought a lot about these things. So they look at what are called randomized Quasi-Monte Carlo methods, and the way these things work. So again, there are like a couple of books already on that stuff. So they take existing QMC constructions like this Van der Corput or whatever, and kind of try to inject some randomness, right? So maybe you permute the coordinates. So like flip role of x and y, or do some other like fancy permutation depending on like the structure of that thing. Right? So again, kind of they are, somewhat like tailored to those constructions. So again, but using very specific points. Right? And so it's not been very successful. I mean, there is, they get around some limitations, but suffer from many others, and I'll discuss as we go along some of these limitations. Okay, so what do we show? So we'll give a randomized Quasi-Monte Carlo construction, which will do the following. So the first thing we'll do is we'll be able to go beyond this Hardy-Krauss variation. And I'll explain in the next slide what I mean by this. And in particular, we can get much lower error than what's given by these Koch-Spann-Halavka inequalities of this type. Okay. And the second thing we'll see is our construction has like much more desirable properties. Like first, it will only use random samples instead of these very carefully constructed points. It will combine the benefits of MC and QMC in a completely automatic way, which I'll describe, and it's also fast in some sense. Yeah.
I was wondering whether all these approaches decompose the error using Cauchy-Schwarz, because if there is, that may not always be tight, especially if the points are random.
Okay, great question. Yeah, hold on that thought. That's exactly what, we're going to exploit. Okay. Yeah. Good. But you're like 5 slides ahead, so great. Okay. Good. So let me just describe these results a bit more formally. So the first thing we do is, instead of this error which was given by this Hardy-Krauss variation, we define a new notion of variation, which we call smoother out variation. We'll see in a sense soon what it is. But it's kind of much better than this Hardy-Krauss variation. And maybe this is surprising because, in general, these inequalities are tight. Right? As I said, like if you fix a set of points, I can find a function that does bad. And of course, the way we'll be able to improve this is because our construction is random, so you can hope. But in general, so maybe this is a more TCS way of looking at it, and maybe people didn't look at it too much. Yeah, and as you'll see, like even if you allow randomization, it's not really obvious how do you improve this. As you said, because we'll have to see where that Cauchy-Schwarz is losing and somehow exploit it. And that's why like most previous QMC works kind of stuck with this Stokes-Markov inequality. Right? Yeah, in some sense, it's like the first improvement. There have been like one or two works which kind of try to exploit this, but they have a very different focus, so it's not really comparable. Good. So let me tell you what this smoothed variation is, and it's probably the slightly technical slide, but hopefully not too much. So it'll be convenient to look at all these things, really two quantities we care about. This is Hardy-Krauss variation of a function and this. And we can kind of look at them conveniently using Fourier analysis. So and again, we'll just look at 1D functions. So I can write any function in this Fourier basis. So as we know, like the standard deviation is just like the variance is just the sum of squares of Fourier coefficients, except like mean is subtracted out with the 0th coefficient. The Hardy-Krauss variation also has a very clean formula because what was this guy? This was just the L2 norm of your f prime, right? And f prime has a very nice Fourier representation because it's Fourier coefficients are just k times f hat k. So you get this k square. Okay, this is just Parseval. So great. So smoothed out variation, you can think of it as replacing this k square by k. So it's a much smaller quantity. And again, just by applying Cauchy-Schwarz on both these things, you can see it's always bounded by the product of these two things. So here the coefficients are always 1, here it's k square. Okay, and yeah. So maybe a bit more pictorially, like if I had this particular function sine of kx, Monte Carlo would have given me 1 over root n error because the standard deviation is 1. QMC naively would give me roughly like k over n error, and this thing will give root k over n. Improves the error. So that's one. The second result is that we can optimally combine MC and QMC. So let me say what I mean. So again, we'll construct these point sets so that the error when you evaluate this function is actually this nice thing. So no matter how I decompose my f into like g and h, I can pick kind of mix and match the best of both worlds. Right? So I can pay the MC error for this part g and the QMC error for this part h. Maybe I'll look at an example. So yeah, so it's really improving kind of the bounds. So trivially, right, if I set g to be f and h to be 0, you can definitely beat both. But you can even beat both of them simultaneously. Like so, if you concoct some example which maybe looks like this, then maybe skip the calculation. But both MC and QMC error is like 1 over root n, but this error, if you break it in the right way, becomes like 1 over n. And the nice thing is we don't need to like detect this g and h by hand. And it just does it automatically for you. Like it'll compute the best possible decomposition and get that in. Good. So, and maybe let me elaborate about that point because in practice, and again it's a whole art, like how people use these things in practice. Like in finance industry, they use a lot of these QMC methods. And if you look at their papers, they often say, oh, you should try to never use the QMC just by itself or MC just by itself. You should try to combine them, maybe decompose your function in some way and like apply them separately and so on. So again, what we are saying is you don't need to do this, any intelligence in decomposing it, like our thing will just do it automatically. Yeah.
So you see decompose, I mean, I guess until now I assumed you only have black box access to F, but now, I mean, when you talk about decompose, is it with black box access or you're kind of assuming you have more than that?
Black box. So the way these guys are doing it, they assume you have some white box, because maybe your F is of this form in this region and that, and you decompose it. What we are saying is even with just black box access.
No, so it's a user of black box, but this, like what the finance people are telling us to do, is it black box or is that like requires actually getting into the form?
So from what I understand, it seems to require like as a white box.
Okay.
But I think it's like an intense thing, like they use thousands of tricks and yeah.
Okay.
But as far as, so I think, as far as I understand, nobody like looked at this.
Okay.
Good, yeah. that. Okay, and maybe the final result is, you can get this best of both worlds, but now replaced with our improved notion of variation instead of the Hardy-Krauss. So actually, like one nice thing about that is it gives you a very explicit form for the error, because this sigma SO was this, right, with a k here. And so, in fact, like if you use the Fourier representation, you know exactly how you should split your function, right? Like you should take your low frequency components and put them in sigma SO, because this is kind of oblivious to the frequencies. So you just get something like this, right? You put your low frequencies here and the high frequencies go there. But again, you don't need to know GNH explicitly, like the algorithm does it for you, just with the black box. So that's an explicit form for error. Okay, good. So I think this is a good time for questions about the setting or the results or anything else. Great. Okay, so here is maybe the rest of the talk. So we saw like there are these very good point sets using this Lebesgue discrepancy. I'll try to describe you yet another way of getting a good point set using what's called combinatorial discrepancy. So unfortunately, it's like the same name discrepancy that comes, but this is how historically it evolved. But these are two really different things, but there are connections about them. So combinatorial discrepancy is more about like set systems and coloring them +1, -1. I'll define in a second. But somehow you can use this connection and get good point sets here. And again, this connection has been known since the 1980s. It's called the invariance principle. But it wasn't clear why this is useful. It gives you a nice conceptual way why these low discrepancy point sets exist, but it doesn't seem to help like in practice. So our main idea will be to use some new ingredients that have been discovered over the last 5 years in this area of algorithmic combinatorial discrepancy. And using that together with this transference principle, we can get these new point sets with these good properties. Okay. So I'll kind of spend some time here, and then once we set things up, like the analysis will be pretty easy. Maybe I'll spend like 5 minutes. So this best of MC and QMC will be like completely immediate once we see this, and then maybe I'll say a couple of words about how to get this. Good. So that's the plan. Good. So let's talk maybe for the next 5 or 6 minutes about what is this combinatorial discrepancy business. So this notion was studied by combinatorialists maybe starting 40, 50 years ago. So here you're given a universe of elements, let's say 1 through n, and some arbitrary subsets on this universe. And your job is to color these elements, red or blue, and you want to make these sets kind of as well balanced as possible. Right? So maybe a bit more formally, let's say instead of red and blue, you want to color your elements +1 and -1. And I can think of this as a matrix, right? So given a set system, let's look at the incidence matrix. So the rows correspond to sets and the columns to elements, so 0, 1 matrix. And now if I take a +1, -1 vector x, then A times x, it will be a vector which will just be the kind of imbalance for each row. Okay. So if I look at the infinity norm of this vector, that's just going to be the maximum imbalance. This makes sense. So let's make sure we parse this definition, right? So if I'm taking a +1, -1 vector x and multiplying the by a matrix, I'm kind of multiplying each column by +1 or -1 and adding them. So each entry of my product, if I had equal numbers of +1s and -1s, it will be like 0, otherwise it will be the imbalance. So this quantity is actually measuring the maximum imbalance of your set, and you want to find the best coloring.
Is it really the interval? Oh, it's curly brackets. Sorry.
Okay.
Yeah.
Yeah, so let's forget about the Lebesgue discrepancy. It's just an unfortunate choice of names, but I don't know how to fix that. So this is now the combinatorial discrepancy. And it's just about arbitrary set systems. Coloring +1, -1. Correct. So here is a result that we'll use. It's a classical result in this area. So suppose you have a set system, again on n elements and n sets, but it's like a bounded degree set system. So each element lies in at most t sets. Right? Think of t as a small parameter, polylogarithmic or whatever. Or more pictorially, like your incidence matrix is t column sparse. Right? So each element lies in at most t T sets. Then you can actually do much better. So again, like if you just did a random plus minus coloring, you would get like your rows can be very dense, so you can't really be too dense. But there is this nice result in this area that you can exploit column sparsity to get much better, like depending on T. And maybe I just put this historically. So this thing was very easy result, like proved by Beckerfield in the 80s. And then there was this major breakthrough using sort of non-constructive techniques by Joel Spencer, which got this bound. And there was like even bigger breakthrough using convex geometry techniques, which got this. And this is the best we know so far. And there's like this big conjecture in this area that the right answer should be root T.
How comes it's M does not appear in the bounds if you take all subsets of the size T, then it's not good?
Oh, because your T will be very large. Your T is like how many ones are in each column. So good.
It's not the way around.
Yeah. So maybe like the picture to keep in mind is maybe your set system is kind of maybe dense rows, but like columns are, say it's the incidence matrix of a graph, for instance, with like two stars.
I suppose it's transposed.
Yeah. And we'll see why this is useful. So I won't prove this, let's take it on faith. Like it's actually like beautiful proofs. So let me define this one problem that will play a major role in this thing. It's called Tushnadi's problem. I studied from the 80s. So it's a combinatorial discrepancy problem. And it's the following settings. So I'm given n arbitrary points now, let's say in a two-dimensional box. So again, I want to emphasize the points are arbitrary, right? Not to confuse with the picture where we are trying to place them uniformly. This is like completely arbitrary points. And I want to color the points +1 and -1, or red and blue. And what I'm interested in, I want to do it in such a way, like a fair way. So if I look at any rectangle R of this type, which is anchored at the origin and somewhere, then they're like exponentially many such, like infinitely many such rectangles, but or maybe n to the 4 of them, or whatever. Then you want to minimize the imbalance over all such things. Okay, so is the definition clear for this? So I've just given a bunch of points. I want to color them to make sure none of these rectangles is like very unhappy with the imbalance. Okay, so again, random would be very bad, right? If I just color points randomly, but I'll show you that there is an easy way to get log to the 4, like super easy. Yeah.
So in the previous slide that we had this T parameters, if this, like the points that are at the bottom left, they're in almost all the rectangles, right? There was like the.
Yeah,
So
okay,
it's a little bit
good.
different.
Yes, okay, so maybe that's it, yeah. So let me try it. So, alright, so we have these endpoints, and we should think of it as each rectangle corresponding to like a row, right? So naively, if you think about it, like maybe this is not column sparse at all, because this point could lie in like many things.
The points in the bottom, like near the word.
Yeah, like this guy will lie in like almost every rectangle. So, but here is a trick. You can use dyadic decompositions, and we'll see how you get a polylog. So the idea is, let's just look at the one-dimensional picture first. So take the x-axis and decompose it into like intervals of length, half, quarter, 1/8, and so on. That's up to 1 over n. Good, and let me do the same on the vertical things. So each of these like dyadic intervals now will define a dyadic rectangle, right? Like take one interval here and one dyadic interval there, and let's just stare at it. What happens? So each of these rectangles are arbitrary rectangles are. I claim you can express it as a disjoint union of log squared dyadic rectangles, right? And maybe let's just see in this first dimension, because if I look at any prefix, I can write it as a union of log n different many intervals, and I do the same in both dimensions, right? So the cross will give you log square n. Good, so this is trivial. Okay, so basically it says I can just try to control the discrepancy of these dyadic rectangles. I'll take a log square here. Okay, but now if I look at these dyadic rectangles, I have another great property, that each point in my space only lies in log square n dyadic rectangles. And let's just see why, because let's look at the interval case. So if I look at any point here, All right, let's look at this point. It will only lie in like some, one rectangle at one interval at each level, right? So line log n, and so the tensoring will tell you it lies in most of them. So that's it. So now if you look at dyadic things, then it becomes a column sparse thing with log square and sparsity, and I can use this vector.
These are defined with respect, some arbitrary set of points, you're just gonna number them 1, 2, 3.
Yeah,
So
yeah. Or you can break uniformly 1 over n. It won't matter because that Lebesgue measure hardly changes. Yeah, okay, yeah, you can do it in any sort of phase. Right. Yeah, let's think of numbering these points. And actually, depending on how you break, yeah, like people can have tried to improve this and speed off some more log factors. Okay. Okay, so I'm mentioning this Tushnadi problem, and it's not clear why I'm mentioning this. What does this have to do with anything? So now let's connect, this world of combinatorial discrepancy to this Lebesgue discrepancy about placing point sets in a uniform way. And this is called this transference principle. And the idea again is very simple once you see it, but it's like an amazing idea. So what I claim is that if you have a good algorithm for Tushnadi's problem, and we saw like this log to the 4n. So let's even look at that trivial. Right, so for a 2D box, we saw this log to the 4n thing. You can use that to get this Lebesgue discrepancy thing. So again, in Lebesgue discrepancy, I want to place points uniformly so that the volume minus the number of points. So it's like seems completely unrelated to the combinatorial discrepancy. But let's see how. So again, the idea is very simple. What I'll do is I'll start with a lot of points. Let's say n square randomly thrown points. We'll see why n square comes. And then I'll apply my Tushnadi's algorithm. So I'll maybe like take my n square points. I'll apply Tushnadi to color them red or blue. And then I'll use that to, maybe I'll just keep the blue points. Okay, that will help the animation. So, right. So then I'll have roughly n square over 2 points. And I just keep doing this iteratively until I have n points. So I'm kind of using combinatorial discrepancy to sparsify my n square points like again and again until I just get n points. Yeah, that's the whole algorithm. So I claim that once I start from n square and I have just n points left, that the Lebesgue discrepancy of what I have left over in this sparsified system is only this alpha n or like polylogarithm. So let me just give you a proof by example. Let's just focus on like one rectangle here, right? Whose discrepancy I care about, like how many points land up there. So the left half. So initially when I threw n square points, right, on average I expect n square over 2 to land in there, plus some standard deviation of square root of n square, so n-ish, maybe imbalance. Right? So initially I'll have these many points. Now when I apply Tushnadi to color them red and blue, so Tushnadi, right, will take the points here, split them into half, but roughly it'll guarantee it's almost the same, up to like a plus minus alpha and such factor. Because that's what Tushnadi did, like it colored the points red and blue, so that for every rectangle you have this like miraculous property. So these points will halve now after round 1, I get n square over 4, this will become n over 2, and I'll get maybe imbalance because of Tushnadi. But then I apply again. I take that distance, apply Tushnadi again. So this thing will now halve, maybe I'll get a new error in that round, and so on and so forth. And you see where it's going, right? So so you kind of get a geometric series here, so you don't pick up too much. And that's easy exercise. So after log n rounds, you have n points, and your discrepancy is like amazing, like n over 2, what you expect, plus maybe like this alpha. So in fact, this is this general principle of using combinatorial discrepancy to sparsify things and get like desired properties for balance for various sets and so on. Okay. And okay, maybe this looks inefficient because I start with n square points and I'm just left with n points, but you can be smart. You don't have to throw away the other half. You can actually use both, right? Take the red and blue and because the other part is also good. So both those are good. So in fact, like when you apply this with n square points, you actually get n good sets of n points each. Good. Okay, so I kind of really like this argument because it gives a nice conceptual proof of why these low discrepancy point sets exist, right? Because van der Korpert, okay, it's just some construction, you can do the calculation, but what's really happening? But in some sense, this is more conceptual. And again, this was known since the 80s, but then you can ask, why bother, right? And there are already very good point sets, so why do you go about this roundabout way of constructing these things? And so here comes a new ingredient, which was our idea. So let me make one more definition than the standard subgaussianity, which everybody knows. So let's say if I have a vector, a random vector with mean 0, I say it's sigma subgaussian. If you look at any projection in any direction, it kind of behaves like a Gaussian, right, up to sigma factor. So that's subgaussian tails. So maybe one, if you haven't seen this definition, like if you pick a standard Gaussian where each coordinate is normal 0, 1, it's one subgaussian. Or if you have Rademacher's, each uniform random one, it's one subgaussian and so on. So here is a result which was developed in this algorithmic discrepancy world a few years ago. And it says, at least in our context, a bit more general, but what it says is that if I give you any p column sparse matrix A, I can, so this algorithm is randomized, called the Gram-Schmidt walk, and it will produce like a coloring, so maybe of your elements. This will be a random coloring coming from some strange distribution, complicated distribution, but with this following amazing property. So first of all, that coloring is going to look like random plus minus 1 basically. It's going to be order 1 subgaussian. Yet, it will behave much better than random in the sense that if you look at this A times your coloring X, right, the entries that you get here will kind of be square root T-ish. So it's like a low discrepancy coloring, right? So it's kind of funny because like the dyadic thing that we saw was to get like a column sparse thing into low discrepancy thing. But they're saying you can get it while ensuring that your coloring is random like or subgaussian. Right. And just to maybe make sure, like if you did a completely random coloring, you would get a square root n here instead of square root t. So even though it looks random, you are still able to get low discrepancy. And not just that, like even if you look at the output discrepancy vector, that itself is gonna be subgaussian. Right? So this will be like a1 dot x, a2. Right. Okay. So again, we'll use this as a black box. It's more non-trivial result. And actually, there was an amazing result which got the best top student paper a couple of years ago, where they took this and designed another algorithm called the self-balancing walk, which is actually super fast to do. So the running time is just the number of non-zeros in A, like this takes n cube or whatever time. And so we'll actually be using this algorithm. But now let's see what all this gives us. So we'll take this as a black box. So here is our full algorithm for producing these point sets. You start with these n square random points in 0, 1 to the d. And I'll just apply this sub-Gaussian Tushnadi algorithm. Right? So instead of this naive Tushnadi that I showed you, I will use this black box to solve that Tushnadi column sparse, with this dyadic decomposition. And so that will produce me these n sets of n points each. And again, if I use this ALS, Alwise, Liu, Sony algorithm, I can do it very fast. So you can show that it only takes like n squared time roughly. So kind of applying the script. Sparsification, I'm getting these n point sets of n with like very good discrepancy for rectangles. Okay. So any questions about the construction? So again, what I'm doing is I'm using combinatorial discrepancy to get these sparse points, but I'm using this fancier algorithm which also gets me this sub-Gaussianity properties on top of just low discrepancy.
Does that help in like analyzing the distribution of the error as well?
Yes, exactly. Good. You're always a few sides ahead of what I want to say. Perfect. Exactly. So we'll see, these were the two main results. We'll see this is like completely immediate, and this I'll maybe say one word. Exactly what we're going to do. Okay, so let's see why the best of MC and QMC. So this point set that I'm constructing, I'm calling it 80 for some reason. It has low Lebesgue discrepancy, just the way we designed it. So that automatically guarantees good QMC guarantees. That's all you needed for that. But also because this sub-Gaussianity thing, 80 looks very random-like. I'm not sure because your initial samples A0 were completely random. And each time you apply this sparsification, it's this sub-Gaussian thing. So it needs like a couple of lines of computation, but you can just show this randomness kind of passes through. So the end thing looks completely random for any kind of test function. Again, okay, let me not say more. Let me keep it hand wavy. Each iteration is kind of random enough because of sub-Gaussianity. So this point sets that I look, it almost looks like it's like a random collection, random points thrown in, yet has low discrepancy. And now we are done because if I write my f in any way g plus h, like I'm doing a thought I'm not actually decomposing it, it's just a thought experiment. And I can always bound the error by triangle inequality by these two errors. And these point sets automatically are better than QMC and MC. So for this I can say I'm no worse than MC error, for this no more than QMC error. So I automatically have that. And this holds for every decomposition. Okay, so good. So that was the best of MC and QMC. Now the second result, going beyond this Hardy-Krauss variation. So let's see why that happens. And this one is a bit more counterintuitive because, as you saw, these Koksma-Halavka inequalities were tight, right? This Cauchy-Schwarz could be tight in general. And maybe I want to say like this observation of taking random-like and low discrepancy has been used in other contexts to get results of the type like best of MC and QMC, but sort of in different settings by some people recently. But this, it's not clear. So here is our idea. So instead of working with this Koksma-Halavka, which applies this like Cauchy-Schwarz, you go back to the Halavka-Zaremba formula, which is the exact formula for the error, and we'll exploit some kind of cancellations inside this using the sub-Gaussianity. And notice, this is completely lost when if you just apply Cauchy-Schwarz, you completely lose that information, right? This bounding by L2 now. So that's kind of really the new idea at high level. Maybe let me just say a couple of things. Yeah, so it turns out like the most obvious thing does not work. So let me just maybe sketch this. Yeah, so I'm going to try to give you a proof sketch of that. So again, here is the Halavka-Zaremba, just in one dimension. Everything tensorializes in dimension. Good. So let's think of this integral as actually like discretizing things. So I'll write this as, so like discretize points. So I'll think of this error as this inner product, right, between the discrepancy of combinatorial Lebesgue discrepancy of these prefixes times this f prime. And you get these normalizations going from integral from 0 to 1 to like some over 1. You know that? Okay, so yeah. So yeah, this is the discrepancy of prefixes. So Koksma-Halavka basically what it's saying, so even if these, so we know these prefix discrepancies are small, right, because we get good discrepancy placement of points. But even if each of these coordinates was, let's say, 1 in this prefix vector, you would still, if you just apply Koksma-Halavka, you get a root n times this L2 norm of L prime. But now if you knew that your prefix vector was sub-Gaussian, you would actually not lose that root n, right? You would gain that. So this kind of suggests, nice, maybe I can exploit the sub-Gaussianity of this discrepancy things to kind of not lose what I would have lost with Cauchy-Schwarz. The only problem is, yes, looks like a great idea. Like when we first thought, we were very excited, but it doesn't work. In fact, if this would happen, this would give you something much better than what I was claiming. And the problem is we only have sub-Gaussianity for dyadic intervals, not for these prefix intervals. So let me just explain by one picture what I mean. Yeah, so these dyadic intervals, when you apply this sub-Gaussian to Schneider and all, you get this great property that that vector is sub-Gaussian. And even though each prefix interval that we are interested in is a union of, say, log and dyadic guys, the sub-Gaussianity doesn't go through, even though this is each is sub-Gaussian. And the reason is kind of what Avram was saying, like, right, so basically what's happening is each of these dyadic intervals has some discrepancy. It's great, it's like each entry is kind of random. But then when I combine them to get these prefixes, I get these very dependent things, right? Because like a point here kind of lies in everything there, and you can construct like a simple example which shows that this prefix vector can be highly like correlated and not sub-Gaussian at all, morally because of these overlaps. And okay, maybe let me just say this. So yeah. So what one can do is like exploit like this more combinatorial structure of dyadic decomposition. And let me just say one thing. So I can express these discrepancy of prefixes as some matrix times the discrepancy of these dyadic rectangles. It is just some explicit matrix which looks like this. So you can write this inner product, right? So DC is P times T. So I can move P on that side. And turns out this P transpose has some nice like combinatorial structure. And let me say that. So P transpose now corresponds to like each column of this thing, and that turns out it corresponds to an interval. And by some Fourier thingy, what you can show is that you get some kind of cancellations of high frequency things. And yeah, I'm hand waving like crazy here, but let's say it. Right. So in some so this quantity improves, and you get something better than Cook's Markov. Okay, so maybe just to summarize, so we saw a new randomized QMC method, which kind of used this old technology which was well known with these new modern combinatorial discrepancy tools which get you sub-Gaussianity. And this has some nice properties, right? We can go beyond Hardy-Krauss. We only use random samples. Algorithm is fast. Automatically combine MC-QMC. Right. And I think the key technical idea was to kind of go beyond this Hardy-Krauss, but not like ignoring the cancellation, but going back to the actual Hlavka-Zaremba formula. So there are still a couple of important open questions, I think, in this area. So one kind of downside, and if I talk to any practitioner, they'll probably tell us to go away, is to get these, we are starting with n square samples and then splitting them into like n sets of n points each. So like if I want to simulate something on, I don't know, like 10,000 points, I have to start with whatever, 100 million something, right? Like it's kind of very weird. Right. So this is kind of not desirable. So, and actually here is a very cool result that came out a few years ago. So if you only cared about low discrepancy for these boxes instead of like the sub-Gaussianity condition, then actually there was this very nice algorithm which starts with like roughly 2n samples and just does some what's called thinning to just get these n samples. So you start with like, maybe let me say a few things. It's a really beautiful result. What it says is you can start with, instead of n square points, just start with like 2n random points. So these are completely random. So let's say if I look at the first half, this could have like a square root n discrepancy here. But then you can just throw like maybe half your points. But this is like a very clever algorithm how you do that. And then your discrepancy just becomes like polylogarithmic instead of root n. Right? So you don't need to start with this n square and classify. So can we also do that while ensuring sub-Gaussianity? Because that would solve our problem. I have no clue like how to do this. Another sort of much more major challenge in this area, and this is like a very ambitious thing probably, is what happens for Quasi-Monte Carlo in higher dimensions. So remember, all these QMC constructions lose log to the d n factor. So like if your d is even just log n, this is like completely meaningless. So then this theory completely breaks down once you go there. In fact, the best we know is just like a random Monte Carlo. We have absolutely no, like in fact, we don't even know an explicit construction that kind of matches, the 1 over root n. Forget about improving it when d is log n. So I think it's like a very nice maybe area where TCS people can have an impact, maybe using pseudo randomness ideas or something. To push to higher dimensions. So let me stop there. Thanks for your attention.
thinking of this through a learning theory lens. So I'm thinking, so the rectangles have like your hypothesis class, and then what we want is some points where sort of the empirical error, empirical distribution matches like the true distribution, either uniformly for the infinity measure or L2 with the assumption of mean squared. So if instead of rectangles you had axis aligned rectangles, you had some other family.
Right.
Then things would change. Like in that picture you had this nice picture that basically looked like a grid but turned and kind of squashed. If my family was like thin, rectangles that went this way,
Right. Then you would want. Yeah.
So I wonder though if the randomization could help to say, hey, you can simultaneously do well, say for all non-axis aligned rectangles, for example, that with larger family and always taking rectangles.
So actually there are results like if your rectangles are not axis aligned, then you cannot be maybe in 2 dimensions like n to the 1/4 or something. So this polylog really comes somehow because of dyadic and so what that result says if you allow me any rectangle like rotated rectangle, then no matter what placement of points I give, I'll at least have like n to the 1/4 discrepancy. Yeah, maybe using randomness. That's not right. Maybe quantifying. Yeah. So right.
Right. So Nikhil will be here at tea time at 3 o'clock. One more question. Okay, one.
So I had one question. So you said so you were using some black box result in which there were 2 bulleted points, and the first one was like something is sub-Gaussian which you kept using throughout. So could you remind me like what was sub-Gaussian? If I understood correctly, it was the number of points in each dyadic set. Was that random variable sub-Gaussian?
Okay. So you mean this Gram-Schmidt work? What guarantee it gets you? Yeah. So think of it in this way. So it's guaranteeing you the following 2 things. I have some matrix A. Right. So in the regular discrepancy, I just want to find like a vector x, so that these entries are all small. Right. This is my discrepancy. But here we are kind of guaranteeing you not just that these entries are small, but 2 additional properties. First, your coloring looks kind of like it's a random coloring. So that's this thing. And the second property is, even if you look at this output vector Ax, this also looks random. Right? And in our analysis, maybe it was too quick, kind of both these are crucial. And some of this is crucial when you add these prefix intervals, you kind of can add in a L2 way instead of L1 way if you have this person.
Also, the second question is, what is Q in QMC? Like, how does it, what's the...
My Quasi, I mean, they chose that 50 years ago. Yeah. Right.
I think it's to contrast with pseudo.
Yeah, maybe pseudo was tech.
Oh.
I should look up the history. By the way, one more thing. So on this Quasi-Monte Carlo, there are very nice Wikipedia pages also, which is how I first learned about this. Because if you try to read these books somehow, I get lost. Yeah, somehow very technical.